All right, thank you, Dimitri, thank you, Andre, and all the organizers for the invitation. This is super fun. And I think that I'm gonna touch upon some of the questions that have been asked to Dimitri and then Andre before in my talk, but taking a completely different approach to these ideas of music and geometry and mathematics. So my approach is based on networks, and for those of you who are not familiar with the concept of networks, we'll talk about it very briefly later, but the talk is organized basically on these 3 papers that I published in the past 4 or 5 years. This one on the Leonardo Music Journal, before they merged it into the Leonardo Journal altogether, that introduced the idea of networks and music. This one that goes a little bit deeper into the definitions and the properties of the approach that was published on the Journal of Mathematics and Music. And the last one that addresses some of the questions that Andrei was talking about, the concept of complexity and how we can relate this to music. So to start just briefly, we are all very familiar with networks. Networks are ways of representing data that have relationship within each other. And this is a classical example of a network. This is the, I think, Delta Airlines a few years ago, the map of all the airports and connections between airports. And so a network is defined by nodes, that in this case are the networks, and the connections that are the links that connect different nodes. Networks are ubiquitous. There are different examples here. And they are useful because you can actually infer a lot of information from the network structure, and there is a whole science of network that is being developed in the past decades. So in my talk, I'll be concerned about 2 properties of networks. One is the degree distribution of the nodes. That means how many links point to the same node, and how this degree distribution is shaped, in particular if we analyze music using this technique. And the other one is a measure of community structure, where community structure means how we can group nodes that are similar with some definition of similarity or distance, for instance, and what this community mean in the context of a musical approach. So if we look at this particular example, this is my Facebook network when Facebook was allowing us to download our own network representation. And you see here the examples of both this degree distribution. You have nodes that have higher degrees than other ones. And the one in the middle there is not me, it's actually my wife that is connected to many of my friends. I'm not in this map. But you also see how there is a community structure that develops. And so all these kind of blobs group together friends that have similar characteristics. So these are all my musicians and composer friends. This is kind of family. Up there somewhere is the physics community and so on. So kind of, this is the kind of geometry we are working within. So how can we use this kind of representation when we talk about music? Okay, my point here is that you can use this representation in basically every kind of characteristics of music. You can use networks to characterize melody, to characterize harmony, rhythm, orchestration, timbre. And I have examples in either some of my papers or the website, and I just developed a large Python library to work with this concept, so you can actually have examples of all this in those in that library, and I'll give you the links for that. But today, and most of the work that I've done in the past years is based on looking at harmony and mostly in the Western classical music tradition. So I will be talking mostly about vertical structures, but you'll see how this kind of builds into this larger space of music. So we will kind of connect with what Dimitri has talked about and Andrei was talking about. So I will go fast here, or maybe I should go slower, but I think this has been covered already. We work with 12 pitches of the chromatic scale in equal temperament. Well, not necessarily in equal temperament though, because one of the reasons why I started developing this concept was to extend or to find representations for different tuning systems that are not part of the official, common practice study of music. Anyways, I'm interested in this talk in particular on how we can combine pitches in different groupings of different cardinalities. And so I'll be talking about what I call the harmony space. That is the vertical arrangement of multiple 2 or more notes. So how many chords can you build if you have like a 12-note space or a 24-note space, like if you add quarter tones, for instance, in your equal temperament system, or if you want to build chords using 88 keys of the piano keyboard, and you see these numbers, they become exponentially large. And we are talking about superposition of notes without repetitions. So it's not C, E, G, C, next octave, that's just C, E, G. So in this kind of space, we can build a geometrical model where chords are vectors with components, so they are vector of different cardinalities, length. We can define distances in this space, like Euclidean distances in the very simple example. And once we kind of put together all this information, we can build a network where the nodes are the chords and the edges are defined by a distance. Now, this is completely deterministic. I'm using all the possible combination of n length vector chords when I build this space. And so it's a way, in some way, this gives you a representation of all the possibilities that a composer has, for instance, to build different progressions. So this is an example of a network for a 24 equal temperate 24-tone equal temperate system with each node at the distance of just 1. So that if I take the vector of, and this is for the triad, triads, I think, or tetrachords. Anyways, the idea is each link between nodes correspond to just changing one of the nodes by one semitone. That's a distance of 1. We can do this on the space of the triads in the 12-tone equal temperate system and look at different distances. So these are maps, in a way, of all the possible transition from one triad to the next triad by changing one semitone, 2 semitones, or 3 semitones, and so on. They're interesting from their topology and the fact that actually these are kind of navigational maps. If you want, you can go from one chord to another chord, and you can follow directions in this in this space. Yeah, I think this is kind of the message here.
Marco, what's the meaning of the color? Green.
The colors are the community structures that are identified by a measure on the network. So it's not I'm not coloring anything. This is colored automatically by the algorithm that checks for the similarity structures. So this might not be very interesting per se, but it's a very nice, a useful classification tool. This is from a paper that I don't really want to discuss too much, but it's a study where I looked at the relationship between particularly tone rows of 12-tone music, and it's inspired by a paper from 1977 by Morris and Starr, who are like Robert Morris is a famous musicologist and music theorist, where I kind of was able to do a classification of these particular musical structures. But this is not yet a composition. This is a kind of a catalog, a kind of a classification scheme. The point is that when you have this deterministic network, but you are extracting chords in a composition, what you are doing is actually going from a synthetic network, deterministic network, to a complex one. So you are introducing complexity because among all these possibilities, you are choosing a path. And so this opens a kind of a two-way thing. On one hand, you can use this to represent a piece of music through this representation. On the other one, it becomes a very interesting tool for composing. And I will get back to this in a little bit. So, as an example of what happens, this is a network representation of one of the chorales by Johann Sebastian Bach. And we can see how in this representation the composition evolves. And this will be very loud. We seeing here? So we see, first of all, a map. So this network maps all the chords of the score. And I'll show you how this is done in one of the next few graphs. But the most interesting thing to me was when I did this and I applied this algorithmic search for communities. The communities came out with these different colors, and as you heard in the chorale, these identify different tonal centers, different keys that are present in this particular chorale. And this is not something that I did. This comes straight from the analysis of the community structure using one of these algorithms that actually a good friend of Dimitri and I, Mark Newman, very famous network scientist, has developed over the years. So there are, ideas, concepts of distance here. There are transitions. So you see that some links, all the links are directional. So you have arrows that point to this chord goes to that chord, and that goes this one and that one, and so on. So these are the links now, and the width of the line correspond to the frequency with which that chord goes to the other chord in the whole composition. And so you see, for instance, some directions, some links are asymmetrical. There is a higher occurrence of a chord like this one, E major, to go into A major than A major to E major. And we'll see this as is an important property that we'll discuss more. So this is this was the first realization of this idea. Then I went and worked more on more complex pieces. And so this is an example of one of the Beethoven string quartets. It seems that we are going back to Beethoven very often this afternoon. And here is kind of the way in which I extract the information that is then mapped into the network. So each vertical section of the score is mapped into a vector, and then the sequence is the sequence of the vectors, and each vector corresponds to a node, so repeated vectors correspond to the same node, and so on. So the score network is built in this way. Now, the score network has, I would say, four kind of topological characteristics that, there is a certain degree distribution. You have nodes that are bigger because they have more connections. And so the diameter of the node is actually important here. There are the colors that correspond to modularity classes. That means communities that have similar characteristics. There is a directionality of the links, so these are directional networks. They are not like general networks. And within the modularity classes, you still have some sort of relation between the nodes that hints to some sort of degree distribution within the same class. Well, if you put this one on a log-log plot, what happens is that these networks appear to be scale-free. So in a way, they connect to fractals and the fractal geometries that Andrei was talking about. But what is more interesting from my point of view is the fact that these scale-free properties are actually very much connected with general properties of tonal harmony. So tonal harmony is governed by a few central chords. These are the hubs that we have here. There is a hierarchical structure that is mirrored by the degree distributions. There are preferences for asymmetric chord progressions. That means the reactional networks with preferred directions and so on. And then you have this different modularity classes that identify groups of chords. Now, if you take this picture and now you map it into a time series, so you do the same kind of analysis, but now you put everything as the sequence. So this is what happens in the piece. I'm not abstracting from the structure. I'm keeping the structure of the musical piece in time. Then the mapping is a tokenization, basically, of these vectors into single numbers, integers, that I can plot. And I can look basically at the representation in a way of the dynamics of what happens in the composition. Now, time series, we can analyze them in millions of ways. In this particular case, I'm using a segmentation algorithm that I didn't invent. It's just I apply this segmentation algorithm from this particular library in Python, and I get sections that seem to correspond to very specific units of time or parts of the composition, and each of this section is itself represented, can be represented by a network, so that you look at the network that happens in the first section, then the second section, the third, the fourth, and so on. And if you zoom in, you immediately realize that these colors or these sections correspond to very well-defined musical regions that correspond to a particular key. So all this is in E flat major, and with the typical distribution of degrees and links that correspond to this particular area, and then you get to the next section that is in G minor, and you see that there are common chords. So there are same chords in the same, that are connected. You see these lines here but now the importance of each node has changed. So you clearly see that the bigger diameter is the GB flat D rather than the E flat GB flat. So it becomes a very powerful way of looking at the evolution of a piece in this tonal context that allows you to separate different parts of it. And this, again, is completely automated. I'm not doing anything. It's not controlled by me in any way. I mean, the only thing that I'm doing is run these algorithms with this particular input. Now, I want to go very briefly into the compositional aspect, because after all, I started to develop this because I wanted a different compositional tool to work with for my compositions. And this is somewhat a kind of prelude to the first piece that we will be watching after my talk for this music presentation that explores these ideas in depth. So let's go back to one of the backchorals. This is a different one, but doesn't really matter here. And look at the network in terms of the optimal path that I can travel in the network in order to go over all the nodes. So a typical optimization problem, route optimization, Postman problem, and so on. So it looks like, and I have other data, not in this presentation, but I could show it. It's in one of the papers that I was showing at the beginning, that the backchorals are really optimal in terms of the routing optimization problem. So you have here the original back routing, and this is the one that is found by the algorithm for the optimization of the solution. But this kind of concept here is what allows me to use this idea of networks in a compositional context. So for instance, I can generate a network that has the same topological characteristics of a backchoral. Say these networks are developed in the late 90s by Albert Laszlo Barabasi and Reka Albert. They're called the Barabasi-Albert model of scale-free networks. You can generate them very easily on a computer. You have a degree distribution, you have links. What you can do, you can take a chord distribution, and in this particular example, I take the same chord distribution that is used by Bach in his composition, and I put it there, basically matching the degree distribution of the original with the degree distribution of the generated network. And I ended up with the original and the generated score that I think we have time to listen to. So this is the first one is the original, and this one is the generated. clearly there are, there are parts where the fact that you have these hubs, these large degree nodes, makes the music go in that particular direction. And since the large hubs are the more important chords, you maintain some sort of a kind of a tonal feeling of the piece. It's probably not what Bach would have written, but that's, I generate another network, I get another series of chords. So these ideas are at the basis of the composition you will hear momentarily, but I can talk, whoever is interested, you can ask me how these are used. Okay, so now we go to the complexity of music question. And so over the past 4 years, I've been leading a working group at the Santa Fe Institute where we have started to study and explore this idea of music complexity. We had 3 meetings so far, lots of fun, many different people. Dimitri is one of the people that attended all the meetings. We are now starting to create guest editing a full issue of Advance in Complex System journal on music complexity. The call for papers is not out yet, but I'll send it around when it comes out. And also a online course for the education programs of the Santa Fe Institute on music complexity. But okay, I think Andrei mentioned at a certain point in passing this idea of measuring complexity through information theory. Here, what we do is basically consider entropy as our measure, so entropy of information, and we looked at 2 different measures of entropy that I'll show you momentarily. One is the traditional Kullback-Leiber divergence, and this is all built on the network structure. So basically what we are doing, we are looking at the conditional degree matrix, that is something you can get out of a network, and you use that as your descriptor for the system. The other one is a method that's been developed by a colleague of mine, Paolo Grigolini, that is called diffusion entropy analysis, that is based on a time series. So kind of, if you put together the KL divergence and the diffusion entropy analysis, you have, kind of the network representation and the time series representation of the pieces, and then as a comparison, something that is not related to a network structure, but is something that we started to look at recently, is the computable information density using data compression algorithms. And for this, I'll show you some of this data. They are not based on networks, but these are based actually on the Spotify, so real audio information. Okay, so results. I should say here that when we use this kind of techniques, we are not trying to get a number for a piece. What we are trying to get is a trend that we can use to analyze, say, the evolution of a genre or the evolution of something, because we are looking at hundreds, thousands of pieces with a statistical distribution of these measures. And clearly, within the production of a single composer, you might have some pieces that measure very high or very low, depending on say, the movement of a symphony or a sonata. But the important thing here to look at is how these measures evolve in time. And this is the diffusion entropy analysis done from Josquin to Mahler. So one of the problems here is that I think it was mentioned earlier that we don't have enough data, I mean, a lot of data that we can use. So it's difficult to kind of generalize this in a broad way, but this is the result we get from the diffusion entropy analysis. So it seems that there is a, kind of an evolution of harmonic complexity as we measure with this particular descriptors. So this is for the DEA that correlates with the KL divergence. Here the trend is opposite, but it means the same thing. So increased complexity means going down with this curve.
And the colors?
Sorry?
The colors?
The colors are the different composers. So Brahms, Beethoven, Mozart, Haydn, Bach, Monteverdi, Palestrina, and Josquin. So basically what we do, we take the network structure, calculate the KL divergence, and we get some data here. We use the same kind of representation in time series form, and we do the diffusion entropy analysis. So that looks very much like the curves you were showing earlier, but this is actually the whole sequence in the time series. For the computable information density, we use a completely different set of data. This is the metadata from Spotify. And that is a Mongoose database, because it's what is used for predicting your next song in the playlist and so on. But has some very interesting representation data. In particular, you can get what is called a chromogram of a piece in time. So this is basically a short time Fourier transform of the audio signal mapped onto the 12 pitches of the chromatic scale. So again, this is it's very similar to the kind of abstraction that I was talking about, how I build my networks. There is no octave here, that everything is the same octave. It's all reduced to a single octave. But this is a time representation, so you have at the same time the vertical pitches and the time series of the piece. And you can do this analysis based on this, what is called the computable information density. I think the definition is here. That is basically a measure of complexity based on data compression. So this is a very direct way of calculating these quantities. You take data as they are, you compress them with a compression algorithm. That could be the zip or whatever you use for compression, and then you calculate this ratio. And this is the this computable information density. So if you do that, again you get something that fits with the previous representation that I was talking about. Same composers. I added two of them because it was interesting to look at some microscopic behavior, and more or less you have the same kind of pattern that we were seeing, at least in the KL divergence. You see this negative slope here. It's very interesting because using this kind of representation, you have a kind of discontinuity in Schoenberg, while most of these distributions are one kind of broad Gaussian something. In Schoenberg, you have two peaks. And it's clearly before 1913 and after 1913, when it went into the atonal period. And the measures are very different from one to the other. So this is done with a lot of data. I have to say, a lot of duplicates of different recordings. Within different recordings, you have consistency. So it's very, I mean, if you look at this information density quantification across one single piece, 15 recordings, you have the same value, more or less. I mean, there are very small oscillations. So it seems to be robust to the system. The limitation is that Spotify is bad and doesn't let you download more than X chromograms per day, and so to collect the data takes months because you have to do a little bit by little bit by little bit by little bit. Anyway, this is a work that was done in collaboration with a complexity student, summer student at the Santa Fe Institute last year. Okay, so a few words on my library. It's called Music Network. It's a Python library. You install it from PyPy. It's completely open source. You can get all the sources from GitHub, and contains all the functions that I use to generate the data for this talk, but contains also a lot of other kind of application of network into the musical spaces. So for instance, if you're interested in rhythm, there is actually a kind of a parallel talk I would give, where instead of looking at harmony or vertical structure of pitches, I look at rhythm and in the way in which different rhythm figures interact within a single piece. There is some machine learning on timbre in this library, and also construction of a library of networks based on timbre similarity. So if you have a large set of samples of different instruments, you can build networks like that. And there are also various tools for more composing tools and so on. And last but not least, this is my website, and thank you for your attention.
Okay, well done. 1 minute to spare. Who has questions? We have Mark in the back.
Thank you very much. First of all, it's fascinating stuff, all kinds of different interesting things to explore. Can I be a colossal bore?
Yes.
A question about evaluation, which is the thorn in the side of a lot of projects, certainly mine included, particularly when there's free composition. How do you know whether you've done a good job? It's a totally open question. There are tractable parts though, and I wondered if you've gotten into that in any sense for example, the entropy measures. What would it mean for you for the entropy measure to be accurate? And then likewise, the segmentation methods. We've experimented a bit with ruptures and some alternatives. Do you have a defined sense of what it means for the segmentation process to have worked effectively? Maybe it's, in this application, it's the same as segmenting by tonal region. So if you move into a different key area, you have a new section, and maybe that's fine. Or maybe is there a need for human analytical? So
if you are talking about the segmentation algorithms, you always have a threshold, right, that you can control. And if your threshold is too high or too low, you might have like just one section or like 25 sections.
Right, that's for sure.
You have to find, there is no loss function that you can use because you don't have a reference.
So that's kind of the question, yeah. Do you think you need a reference? Do you think you need something external to measure that again?
What I find is that, I didn't work on, I didn't look at an enormous amount of pieces, but there is some kind of a sweet spot that allows you to segment in kind of the right way, in the sense that each segment corresponds to a particular key, but I'm pretty sure that it's very much dependent on the style, or actually on the general over kind of higher structure. So if you look at all tonal pieces, you probably have a threshold that can vary by very little. But then if you go and look at other things, you might not be able to kind of segment according to some other measure that you might be interested to. So, for instance, I did some analysis of Ligety's preludes. So you take disorder, for instance. It's all over the place. Clearly you can't separate like, oh, this section and this section.
Yeah, maybe not on harmonic grounds.
Yeah,
maybe there's something else.
There is something else, exactly. But this is what I was saying, like, this is just one little phase of a multi-phases die. right? You can look at this one here, and then rhythm there, and timbre there, and then you have to put everything together. But I find that in my compositional practice, I use these things way more than, I mean, I'm not a music theorist. I'm very interested in these universality structures in a way, and that's my physics background, I think. But yeah.
Thanks. And you are a music theorist, by the way.
Well, not as accomplished as Dimitri.
So I'm kind of interested algorithmically in how you gather up the notes into a chord in the actual sort of...
Oh, that's actually thanks to a friend of ours who wrote another very good library in Python, Mike Cuthbert at MIT, who wrote this library called Music21 that has a function that's called chordify that takes this XML score and just slice it. It's what another friend of ours, Ian Quinn, calls salami slices.
And
So
do you have
basically
any
do a
idea?
salami slices the chord.
Is it just segmenting on the beats, or do you have any...
It's segmented on any note change.
Oh, it's every note.
Yeah, and it's quantized, so you can change the quantization. So you can say, okay, I want every quarter, I want every 8th note, or I want every whatever, 16th.
Okay.
Yes.
So in your generation, in your generated music coming from the network, how did you choose the rhythm? Because this is just the chord sequences.
Well, because I can, because I have networks for rhythm also that I can build.
So you had another network.
Yeah, there are networks for chords, for rhythm. Actually, the way in which some of the ways I use, for instance, is I generate the network with the chords, but then I split the chords, and then I use different rhythmic networks for different parts. And maybe some of these things will come out from the performance we're going to hear soon.
And I wanted to follow up with what are you doing with deep learning?
In this library there is a very simple. I use a convolutional neural network just to do timbre recognition given a distribution of samples. So I can recognize if the sound is produced by a metal object or a wood object or a plastic object or cardboard or whatever. And was part of a research project that I did during a sabbatical and residency in France in 2019.
More questions? I have a question.
Yes.
So, Marco, we've talked about this before.
Many times.
Do you have any ideas about how to make the analysis more hierarchical? Maybe looking for chord, like higher level key networks, and then chords.
Yeah. That's kind of the one possible idea. So, in one of my papers, I'm proposing like this segmentation in key areas. Algorithm to identify the key area and then apply existing, for instance, numeral analysis software like the one is Music21. I mean, unfortunately, these algorithms are not very good. But I mean, in principle, you can if you identify the key and then you feed the key to the function, then the function tells you, oh, this one should be a, I don't know, minor 2 or something.
Would it be possible? I think it could be really useful to build a kind of very general purpose, stable pitch finder. I'm imagining something like I can improvise, and if I'm sitting on 5 notes for a long enough time, the algorithm will sort of realize, oh, that's a stable set of notes, but maybe it's not bound to specific keys or bound to specific...
I think that there is a tool, it's called Melodyne, that is part of Pro Tools, that is very sophisticated. It can give you all this kind of information. I don't know if real time, but I mean, this is what professional people use for pitch corrections from singers.
Right.
So that's probably a way of looking at those things. Yes?
So how much longer will it be before you can generate a new Bach piece that is nobody would know was not written by Bach?
I mean, there are already examples of that.
Okay.
But as Dmitry was saying, most of the AI things they don't work very well, and the one that they show you that work well are hand-picked examples.
Well, so I'm asking though, how long will it be before they do work well?
I mean, I don't think very long,
Okay.
but the point is, and this is a very long discussion we will have over beers,
Okay.
but the point is that as composers, we are not interested in regenerate music of other people.
No, I understand that.
Right? So
That wasn't the question.
one of the best, the sweet spot, as another friend of ours, Amy Howard, who's a composer here in England, in Manchester, she says that the most important place where you want to be is when the network is not trained yet, and so it makes mistake, and then you use the mistake as your tools or pieces that you can put together and build a composition. Who cares? I mean, I don't care to create a new Bach choral, and there are tons of students who have done that for generations. So that's the idea. Okay, so I think we go to the next part, right? Yes. So in the next part, you have the program notes. These are 3 audiovisual pieces. The first one is the one I was mentioning, is mine. Then we have another piece of a friend of ours, David Stout, who's also part of this working group at the Santa Fe Institute. And then a piece from Dmitry, where I think, you can see some of these ideas that he talked about in action. So, let's do this here. Can we get the lights completely off? Yeah, I have no idea what happens with the... No, just completely off. Don't worry.
We can control the volumes on the video, I think. So we should
Can we?
maybe do a volume check before we...
I don't know if we can control the volume.
No, but look, you've got a volume slider right there.
That doesn't mean it works.
No, it works.
No, here it seems to work, actually.
If it's connected to HDMI, it often doesn't work.
Really?
Yeah, it really is.
Which is ridiculous.
Well, we'll try.
No, that should work. That's before it goes to the audio house.
Well, it's fine. Just asking because we want.
Yeah, everything goes to work.
Start it again now. Start it again.
Yeah, this one works. That's very good, actually.
Parmi la foule immense à multitude immense, je marche de rue, de granit. Avec longtemps
I walk through the streets of granite. I walk through the streets of granite with the intense solitude that breaks, with the intense solitude that breaks beyond the infinite. Cammino in vie di granito tra una solitudine immensa, con l'intensa solitudine densa, poco palente. Cammino in ruas de granito, cammino in vie di granito tra una palente immensa, con l'intensa solitudine che rompe l'infinito. Je marche dans rue de granit, parmi la foule, je marche dans rue de granit, parmi la foule immense, avec l'intense solitude qui brise au-delà de l'infini. Cammino in vie di granito tra una solitudine immensa, con l'intensa solitudine. I walk through the streets of granite, among the multitude immense, with the intense solitude that breaks beyond the infinite. Je marche dans rue de granit, parmi la foule immense, avec l'intense. Je marche dans rue de granit, parmi la foule immense, avec l'intense solitude qui brise au-delà de l'infini. Cammino in vie di granito tra una. I walk through the streets of granite, intensa solitudine che rompe with the intense solitude that breaks beyond the infinite. Caminho ruas de granito de intensa multidão. Caminho ruas de granito palente de multidão. Intensa palente infinito. Je marche dans rue de granit, parmi la foule de granit, avec l'intense solitude, pour l'intensa solitude que rompe l'infinito. Cammino in je marche dans rue de granit, parmi la foule intensa solitude, avec l'intense solitude qui brise au-delà de l'infinito. Caminho ruas de granit. I walk through the streets of granite, intense, with intense solitude. I walk through the streets of granite, among the multitude, with intense solitude that breaks beyond the intense, je marche dans rue de granit. I walk through the streets of granite, avec l'intense solitude, with intense solitude that breaks beyond the infinite. I walk through the streets of granite, cammino in vie di granito, with intense solitude that breaks beyond the infinite.
Thank you. No, down lights.
Mm-hmm.